We introduced the basic elements of a network graph in a separate video. Be sure to go and check that out. In this video, we will review 3 types of graphs, and it has bearing on how the nodes are connected with one another. How do you think companies connect amongst one another? How do they establish a business relationship? Does it all start on the golf course? Or strictly by searching the web for lowest cost suppliers and service providers? Or do they meet at trade shows? At first, people thought that all these nodes are just randomly connected with one another. It was the mathematicians Paul Erdős and Alfred Régnier who introduced us formally to the concept of a random graph, and it was since also named after them. So the probability of an edge existing is equal. Here we have an example of one such a random graph, and here is another, and yet another. The probability of each of these graphs existing is exactly the same. At this point, it is useful to introduce another network concept called degree. Now, in graph theory, the degree of the vertex is the number of edges incident to the vertex. The degree is sometimes called valency, and if your graph has loops, that is, an edge that goes from a vertex back to itself, then they are counted twice. So if we go back to our random graph and we look at the first example, we see that vertex A has a degree of only 1. It is only connected to E. But B is connected to C, F, and G. So it has a degree of 3. And E has a degree of 4. The degree of a node can be used as an interesting proxy or a metric to highlight the importance of a node. If you were to calculate the degree of each node in a random graph, assuming you have enough nodes in your graph, and you draw a histogram of those values, you will find that the degree distribution, at least theoretically, follows a Poisson distribution. That said, you will rarely find a truly random network in the real world. Next, we look at what is referred to as a small world network. Here we deal with a network where most nodes are not directly connected. We also say most nodes are not neighbors. But neighbors of any given node are likely to also be neighbors. And that is, if I'm connected to Laurie, and Laurie is connected to Aichi, then there is a pretty good chance that I and Aichi also know one another. The small world network is often referred to as the Watson-Strogatz model, giving credit to Duncan Watson and Stephen Strogatz, who identified this as a special case of random graphs. To just touch on the technicalities, it means that the geodesic distance between 2 vertices, that is, the minimum number of hops along connections in this network, grow proportionally to the logarithm of the number of vertices in the network. So what, you may ask? Well, this gives rise to the small world effect in social networks. And I'm pretty sure you've heard of the phrase 6 degrees of separation, right? If not, let me explain. The theory goes that you can connect yourself through social contacts to any other person on this planet with at most 6 connections. There are some nodes in small world networks that have many more connections than others, like D in this example. And these are called hubs. In social networks, we know them too, right? Those individuals that seem to know everyone. Small world networks are commonly found in practice, at least more commonly found in practice than purely random networks. For example, social influence networks, websites, and specifically websites with navigation menus, food webs, and the electric power grid, to name but a few. The third and final network type I will discuss here is called scale-free networks. This means that the degree distribution of the nodes follows a power law. So the majority of nodes have a very low degree, while there are a few nodes with extremely many connections to others. Mathematically, that means that the fraction pk of nodes having k connections, that is, having a degree of k, can be expressed by k to the power minus gamma. And here the credit most probably goes to Albert Laszlo Barabasi, who's currently with the Northeastern University. This gamma typically lies between 2 and 3, but there are exceptions. When the concept of scale-free networks was discovered, it was quite a thing, because you see many real-world networks indeed are scale-free. Protein interactions, social networks, the network of interlinked documents on the World Wide Web, the hardware connectivity behind the World Wide Web, their existence has been established beyond a doubt. But there are two caveats. The first is, not all natural and real networks do follow a power law. So, check. Secondly, there is a valuable paper by Closet, Shalisi, and Newman, who studied real empirical networks, and they came to a smart conclusion. Very few actually follow, theoretically, the power law for all values of k. Instead, you can fit a power law for those k values beyond a specified lower limit, say k min. All these network types, what does it mean? What's the use? Well, Barabasi captured it concisely when he said, a legacy of the scale-free property is the realization that the structure and the evolution of networks are inseparable. Now let's go back to the example of urban freight and urban freight players of suppliers, carriers, and receivers. And say that there is a new carrier who enters the market. The scale-free property tells us that it is more likely to start serving better connected nodes in the network than those with low degrees or few connections. In other words, knowing the structure of the network can help us predict how the network will evolve over time as well. And that is pretty significant for logistics and urban planning.